right, so today we're going to have our first talk of the semester with Henry Adams, and he'll be talking to us about fair division. Take it away,
Great.
Henry.
Thanks, Laura. I'm excited to be speaking today at the Colorado State Data Science Seminar. I'll be speaking on fair division, and my sources are these two articles. Both are very reader-friendly. The first is an article in the MAA, Math Association of America Monthly from 20 years ago by Francis Su. And correspondingly, there's an article in the New York Times from 2014 by Albert Sun on the same topic. So the problem is as follows. We have three roommates, A, B, and C, and they decided to room together for the upcoming year. And their house has three rooms, 1, 2, and 3. We'll keep these colors consistent. So the colors will be the colors of the rooms throughout the talk. So you have the same number of roommates as rooms. And there's a total rent that they owe to their landlord per month. And they need to decide how to divide this rent. So first of all, they need to decide how much each room costs. And they also need to decide who gets which room. And there's no ground truth value for which rooms are more desirable. Maybe I prefer the room with the bigger window, whereas Kyle prefers the room that's closer to the kitchen, etc. And our goal here is going to be to divide the rent in an NV-free fashion. NV-free means once we've made this division, nobody wants to trade rooms. So after we assign the rooms to person A, B, and C, person B is not jealous and would rather have person A's room for person A's rent. The algorithm we'll talk about works for any number of roommates and any number of rooms, as long as you have an equal number of roommates and rooms. But we'll do 3 as our main example. Questions on the problem? All right, so remark is that this can be solved for any number of rooms and roommates. And then an assumption that will later be relaxed will be the following. For the beginning only, assume that each roommate prefers a free room over a non-free room. Okay, so if I have the chance to live in a room for free, my house is of high enough quality that I'm going to take that free room over a room that I have to pay rent for. That's not a perfect assumption, and I'll point out the flaws in that. And also later, I'll point out that that's okay. When we relax this assumption, the algorithms we discuss will still work. Okay, so I'm going to start outlining the algorithm for how you solve this problem. Maybe this is really the setup for the algorithm. And then the proof of Spurners' lemma will be, how you actually solve it. So we're going to draw a triangle of rent divisions. So I've drawn a triangle, and each point in this triangle corresponds to a way of dividing the rent. The topology language behind here is we're using barycentric coordinates. So to specify a point in the plane, you only need 2 coordinates, an x and a y coordinate. But here for convenience, we're gonna have 3 coordinates to specify a point in this triangle. And the sum of the 3 coordinates is always gonna be equal to 3,000, the total rent. So that's the redundancy in our coordinate system. So this first vertex is where room 1 costs $3,000 and the other rooms are free. This vertex is where room 2 is $3,000. And this vertex is where room 3 is $3,000. And then other vertices are linearly interpolated. between those. Okay, so this room, or sorry, this point in the triangle represents the division where, what have we done? We've sort of interpolated halfway between vertex 1 and 3. So the first room should now be only half the price, and the third room should be only half the price, whereas the second room is still $0. Right? For the second room, when I interpolate between $0 and $0, I get $0. This point right in the middle is called the Berry Center. So this is where the three rooms are valued equally, each $1,000. I'll show you some more barycentric coordinates on other parts of this triangle in a slide or two. Questions so far? Okay. Next, we're going to subdivide our triangle to an acceptable level of approximation. So let's say we want to divide rents up to plus or minus $10 per person, okay? Then you want to draw enough triangles so that, you know, maybe this is the true fair division, right? Well, if you approximate that by a vertex nearby, you've only changed anybody's price by $10, and so nobody's going to complain that you've rounded by $10. Okay, so I've done 10 subdivisions, but maybe you want to do 100 subdivisions. Once we've subdivided, I can now maybe label a couple more points on this triangle with their prices. So to go from the bottom left vertex to the top vertex, I need to take 10 steps. Each time I'm changing the price. When I move in this direction, I'm changing the price between rooms 1 and 3. So each time I'm decreasing the price on room 1 by $300 and adding to room 3 by $300. So if I go this direction, you know, I get the new prices where room 1 is now $300 instead of 0, and room 2 is now $2,700 instead of 3,000. Sorry, room 3 is now $2,700 instead of 3,000. This point is where rooms 1 and 2 split the rent. This is a more realistic point where room 1 is $600, room 2 is $1,500, room 3 is $900. So to see that, I could start here, and I notice I take 2 steps towards room 1. So room 1 should go plus 300 to get to 600. And then I take 3 steps towards room 3. And so room 3 should go plus 300 to 900 total. And I've taken 5 steps away from room 2's vertex. So I've decreased the price of room 2 by $1,500. This point right smack dab in the middle, it's not one of our vertices of the subdivision, but that's the point again of equal price between all 3 rooms. Next step, we're going to assign labels of the people, A, B, and C, to each vertex. So A, B, and C are the people. 1, 2, and 3 are the rooms. So if I zoom in, you can see that I've assigned the bottom left vertex to person A, next person B, next person C. And I want to do this labeling in such a way so that every small triangle has all 3 people represented. Okay, so all 3 people are represented in every small triangle, unless I've made a mistake. So now we go through and we're going to poll the roommates. So roommate A, every place where a vertex has roommate A's label, I'm going to ask roommate A, at those prices, which room do you prefer? Okay. Algorithmically, I'm not going to pull every single grid point, okay? But first, let me just describe it as if we poll the roommates for every single grid point. So we go in, and we start asking roommate A, which room do you prefer? So let's see. Down here, down at this point, roommate A probably prefers the blue room because it's free. Okay, so maybe here they also prefer the blue room. Maybe here they prefer the orange room and the orange room because the orange room is pretty cheap. So we go through and we ask roommate A what rooms they prefer at their chosen vertices. Do the same for roommate B. Okay, so roommate B has some room preferences. Roommate C has some room preferences, so let's ask roommate C. All right. And pretend we go through and ask each roommate for every vertex with their name associated to it, what room they prefer. So I should probably describe this vertex. Roommate C, at this vertex, you could have room 1 for $600, room 2 for $1,500, or room 3 for $900. And maybe they say, I'm pretty, I want to save my money, so I'm going to choose room 1. Okay. Often you'll get assignments that look like this. So near where room 2 is very cheap, people will often prefer room 2. Near where room 1 is pretty cheap, people will often prefer room 1. And near where room 3 is pretty cheap, people will prefer room 3. That's not always the case. I'll show you a more fancy picture in a moment. But what we're hoping to find is rainbow colored small triangles. So this is a rainbow colored small triangle. Okay. There's a price point right in the middle here of this small triangle that's pretty close to the price point at these 3 vertices of that triangle, right? So essentially, plus or minus $10 in either way, at this black price point, roommate A prefers the orange room, room 2. And roommate B prefers the red room, room 1. And roommate C prefers the blue room, room 3. Okay? So near that black price point, there's very nearby prices where the 3 roommates prefer 3 different rooms. A, B, and C are 3 vertex labels, prefer 3 different rooms corresponding to the 3 different colors. Do you see that? So that's what we're hoping to find. We're hoping to find a small rainbow colored triangle. And one such triangle exists. Aha, that's how you divide the rent. And if people are arguing over those $10 approximations to bring me from one vertex to the other, you could just subdivide further inside that triangle. Questions
so Henry,
so far? Yeah.
Yeah. I guess then in order to apply Spurners lemma, the idea is, well, say along this edge where 1 is always free, that you could kind of freely switch that lower right corner to be blue, and it doesn't really affect the game, and so therefore the lemma applies.
So I'll mention Spurners lemma in a couple of slides. We'll actually use a variant of Spurners lemma, and that's really all I'll discuss in the talk. But you're right, maybe I should say what Spurners lemma actually is when I describe what the variant we're using is. Yeah. Good question. Other questions? Oh, I see there's a lot of chats. What is that time? Oh, I see. These are about our prior conversation. Okay. Any other questions? Here's maybe a more quote unquote realistic picture of how the polling might go. It's more realistic in the sense that according to this picture, you can see that person B, maybe likes the red room, room 1, more than the others do, right? There are price points where nobody else is considering room 1, but person B still is, right? Nevertheless, under some pretty generic labelings, there still will always exist a rainbow colored triangle. Here there's again only one, I believe. Yep. And that's where our division is going to be. We're going to choose that price point because near that price point, person C, B, and A, the vertex labels, prefer 3 different rooms with the 3 different colors. Okay. So yes, this is a data science talk in the sense that you're pulling roommates, and the roommates can give you whatever answer they want based on the prices and their opinions on the room. But this is also a combinatorics and topology talk in disguise. So the result that says there's always a rainbow colored triangle, meaning a small triangle with 3 different colors, the result that guarantees that is called Spurners lemma, which we'll discuss. And Spurners lemma implies that there's a small rainbow colored triangle, hence an NV-free division, where at that price point, no roommate wants to swap rooms and prices with any of their neighbors. So let's get into Spurners lemma. Well, okay. I'll state Spurners lemma again, the variant I'm using, but here's the variant I'm using. You have a labeling of this large triangle where on the boundary, the labels are as follows. So when room 1 is free, we're assuming for now that every roommate would prefer room 1. And when room 3 is free, every roommate would prefer room 3. And when room 2 is free, every roommate would prefer room 2. Okay, we'll relax that assumption. At the vertices, 2 rooms are free. So you have no control over what people choose between the 2 free choices at the vertices, okay? The variant of Spurners lemma that we'll discuss the most says, if you have a coloring of the boundary of a triangle with 3 colors satisfying these constraints, 2 only, 3 only, 1 only along the edges, and 1 of 2 colors along the vertices, then this variant of Spurners lemma says there's always a rainbow colored triangle with all 3 colors somewhere in the middle. Let's postpone that math for a moment, get to some side comments. So what do you do for 4 roommates and 4 rooms? You have a tetrahedron instead of a triangle. So the 4 vertices are where the 4 rooms are each the entire rent. And then you subdivide the tetrahedron into smaller tetrahedron, and there's a higher dimensional Spurners lemma that works given the assumed colorings on the boundaries. For 5 roommates, you have a 4-dimensional simplex, which has 5 vertices. So we only exist in 3 dimensions, but data analysis exists in all dimensions. There's a New York Times applet. So linked from that New York Times article, you can go through and do this, and you can tell New York Times how many roommates you have and what your rent is. And they don't make you fill out every single vertex in the triangle. They probe you in a smart way. So they sort of, I think what they probably do is they sort of find these divisions where people are deciding between 2 rooms and then follow this crease line until they find a rainbow colored triangle in the middle. So to do this on New York Times, you don't need to fill out the entire triangle. At the very beginning, you might be answering questions like, come on, this room's only $100. Of course, I'm gonna choose that room. But very quickly, the New York Times is really making you think hard. And it's probably frustrating when you answer the questions and then they assign you the rooms, and it's done in an envy-free way. And you better answer honestly, because if you answer one of the questions wrong, your mistake might be taken advantage of by the algorithm. Okay, so that's what I mean by polling efficiencies. You can poll your roommates more efficiently. There's a lot of open work on what do you do when there's multiple envy-free solutions. So what do you do when maybe one person really prefers one room over another, and there's multiple rainbow-colored triangles? I mean, there are ways of saying envy-free is not the only goal, and you could add in other goals. And that's worth looking into. How do you choose between multiple envy-free solutions? There's a whole webpage you can check out. It's called Splitit. And they have algorithms for splitting fares, like for bus trips, cross-country bus trips, for dividing goods. So maybe in a will, watches and jewelry and cars are passed down. How do you divide those goods? You could try to assign academic credit. So maybe, luckily in math, we don't have to worry about this, but author order is a big thing in other fields. So you can fill out how much you think your various collaborators contributed on a project. And then there's I don't know if it's envy-free, but yeah, some version of envy-free division of how do you split up the ordering of the author list. You can distribute chores, who needs to clean the office, etc., etc. Before I get into the math behind Spurners' lemma, any questions?
I wonder if it could be used as like for almost the dual of the problem. Suppose this app sells its data for like renters to see how much people are willing to spend money on that data to sort of maximize their profit as well.
I see. So sort of like, yeah, more matching the rooms to many renters. And yeah, so let me just tell you my non-expert impression of this field, fair distribution. As you change the problem, so here we're trying to divide something that's bad. We're sort of trying to divide the rent, which is bad. Everyone wants less rent. As you change the problem from dividing a bad to dividing a good, the algorithms often have to change on the surface in non-trivial ways, okay? So you might have to use a different variant of Spurners' lemma, or you can't just oftentimes you can't just negate these algorithms and get a reasonable algorithm for distributing a bad versus distributing a good. But algorithms do exist for all these different situations, and there are certainly non-topological algorithms. And I think it's my approach to this area has just been to learn different types of algorithms for different types of problems. And you want to know, roughly speaking, the type of ideas people have, and then how they use these different ideas in different contexts. So I don't want to give the impression that Spurners' lemma is the only tool here, but it's a good tool for 30% of such types of problems. Other questions, comments? Okay. Let me state a variant of Spurners' lemma, and then I'll try to see if I can state Spurners' actual lemma and see if I get that right as well. So you'll recognize this variant because I've already described it. Consider a subdivision of a triangle into smaller triangles such that each vertex is labeled 1, 2, or 3, and such that the following boundary constraints are satisfied. Okay, so along the interiors of the edges, we have only room 1, only room 2, and only room 3. And then on the vertices, you can choose between the two adjacent ones. And then the lemma states, then there exists a rainbow triangle. What does it mean for a triangle to be rainbow? It means it's labeled 1, 2, and 3. Okay, so you label the entire triangle. If you have the following boundary constraints, then there's a rainbow colored triangle somewhere inside. Does the statement make sense? Oh no. Okay. Emily, let's try to state the actual Spurners lemma and let me know if I get it right. So I think the actual Spurners lemma, you just have a different labeling on the boundary.
Right, so you just need to make sure that you have each of the three big corners are a different color. And then
Right.
whatever is on the line between any two colors, it could all be one color or it could be alternating.
Right. Yeah, so the traditional Spurners lemma is not 1, not 2, not 3 on
Right.
these segments, including the vertices.
But
right?
yeah, but then the vertices all also have to be different. So if like the lower, oh right, yeah. So that would work. Yeah.
Yeah. So I think this is the traditional Spurners lemma, and you get the same result. There's a rainbow colored triangle somewhere in the middle. And
Right.
so, I mean, Laura, you were asking, what about if you had to do these other optimization problems? The traditional Spurners lemma is good for some of those other variants. And it actually took people a while to figure out that for this particular problem, you need a variant of Spurners lemma to be able to work. Okay, I'm going to start going through this proof. And the proof is actually going to make this a little bit more algorithmic. So not only are we going to show that there's a rainbow colored triangle, we're going to find it in a fast way, assuming that you've done complete polling. So the proof note that there is exactly one edge on the boundary with label 1, 2. So, this is what the top of our triangle looks like. And if the top vertex has label 1, then here's our one edge with label 1, 2. Whereas if the top vertex is labeled 2, then here's our one edge with label 1, 2. And nowhere else on the boundary of this triangle do you have the transition between room 1 being preferred and room 2 being preferred. Okay. So by the adjacent triangle, I just mean the triangle containing this edge. So the adjacent triangle has either a second 1, 2 edge or else a vertex labeled 3. Okay, so at the very beginning, either of these two triangles, just by our boundary labeling, necessarily it has another edge labeled 1, 2. So here we have another 1, 2 edge, another red, orange edge. Here we have another red, orange edge. Okay. What we're going to do next is we're going to look at this adjacent triangle and continue. We're just going to follow these 1, 2 edges. If you ever reach a spot where you have a 1, 2 edge, and then the adjacent vertex, the adjacent triangle has a vertex labeled 3, then you're done, right? Because here's a 1, 2 edge. If the third vertex of that triangle is labeled 3, that's your rainbow colored triangle. Okay, so we continue to get a path of such 1, 2 edges. Here's our unique 1, 2 edge on the boundary. Look at the adjacent triangle. It should have another 1, 2 edge. Look at the adjacent triangle. It either has another 1, 2 edge or a vertex labeled 3. You keep following these. Okay, so let's see. Right now I'm in this triangle, and here's my, here's my 1, 2 edge. All right. In this particular example, I reach a spot where I found a 1, 2 edge whose adjacent triangle contains a vertex label 3. And that's my rainbow colored triangle. But I need to argue for you that this path of 1, 2 edges always halts. You always hit a triangle where you have the third vertex label. Okay. So this path must end in a rainbow triangle containing label 3. Why? The path can't end on a 1, 2 edge on the boundary. So you can't follow this path and then end somewhere on the boundary at a 1, 2 edge, because there's a unique 1, 2 edge on the boundary. So since there's a unique 1, 2 edge on the boundary, the path can't loop back on itself, since no triangle has 3 1, 2 edges. I should write out the number 3. Okay, so were this path to loop back on itself, right? This path is through triangles that have 2 1, 2 edges, right? They have 1 vertex 1 and 2 vertexes 2, or 2 vertices labeled 1 and 1 vertex labeled 2. So this path is through triangles that have 2 1, 2 edges. It can't loop back on itself because no triangle can have 3 1, 2 edges. And then this path can't go on forever, since the triangulation is finite. So it turns out those are the only other ways that you could avoid having a rainbow colored triangle, right? A rainbow colored triangle stops this path. But the only other ways this path could stop are if it hit the boundary, but it can't, as we argued in the first bullet. If it loops back on itself, as it can't, as we argued in the second bullet, or if it went on forever. But it's a finite triangulation, so you can't want it forever without looping back on yourself. So therefore, this path ends at a triangle that has third vertex labeled 3, and that's our rainbow colored triangle. And you see how this is a little more algorithmic. I was speaking to this. This is how the New York Times is not making you fill out the entire triangle. It sort of finds these creases where different people prefer different rooms and follow those creases until it finds a rainbow colored triangle. Okay. That's a complete proof for the level of this talk. Questions? Good. I want to relax the boundary assumptions. So let me critique. Oh, yeah, Laura?
Can I ask a question? So does it matter how fine you discretize this? So if you discretize it even finer, are you guaranteed to land within the larger triangle you would have gotten if you discretized differently?
Typically, yes. Like for standard roommates and standard roommate preferences, yes. Typically, you would expect the rainbow-colored smaller triangle under the smaller discretization to be inside this one. But in general, no. We're allowing people here to have really weird preferences. They can rank the rooms however they want. In which case, there might be, multiple rainbow-colored triangles, and you might get different answers if you subdivide further, or you might get different answers if you do this algorithm for 1, 2 edges versus for 2, 3 edges, right? You might end up at different NV-free solutions. So yeah, we only find NV-free solutions. We don't choose between them. I'm curious, you could ask a really good question. What are the properties of the NV-free solutions found by this method, right? This method will find at most 3 NV-free solutions. How are those 3 different than the other NV-free solutions? They might be the ones in which individual rooms have the highest prices compared to others or something like that, which might not be a good thing, to be honest. Other questions? All right. Let me critique our boundary assumptions. What's going on? So if you remember, room 1 is red. And I should put it there. Okay. So that line on the side is where room 1 is free. And this is where room 1 costs room 1 costs the full rent. Okay. So I want to critique the boundary assumptions right here. Okay. So this point is where room 1 is $2,700. Nobody's choosing room 1. Room 2 is free. And room 3 is $300. Okay. If room 3 is significantly better than room 2, yeah, I might pay $300 to get room 3 for $300 as opposed to a not so great room 2 that's free. Okay, so my assumption that here I always choose room 2 because it's free is not very good. Maybe room 2's bad room, and so if room 2 is free but room 3 is really inexpensive, I might choose room 3. So that's a critique of our boundary assumptions, okay? All that's needed for our boundary assumptions is that the winding number as we go around the boundary is non-zero. So let me tell you what the winding number is. Let's start walking around this triangle from right here. Pick wherever you want. As I walk around this triangle, I see different colors: red, red, orange, 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 blue, orange, etc. As that's going on, do the same walk on this circle on the right. So on the right, I start at the red vertex. I stay there for a while. And then eventually I go from red to orange. And then I go back to red. Okay, so as I walk around, I see red, red, red. Then I go to orange. Then I go back to red. I keep going to orange. Eventually I go to blue, back to orange, back to blue, back to orange. And then eventually I get back to red and I stay there, okay? So as you walk around this boundary, draw the loop around the circle that you traverse. And as long as you wrap a non-trivial number of times around that smaller circle, then Spurners' lemma still applies. You have to be more careful about the proof, but Spurners' lemma still applies. You still get a small rainbow colored triangle. So let me draw some pictures of that. This would be a picture where I'm at vertex. I start here, I'm at the red vertex. I go to orange. I go back to red. Then I go to blue, and then I go back to red. So you'll notice I didn't walk all the way around, right? So this guy has winding number 0, because I went from red, I went to orange, back to red, to blue, back to red, okay? So here, there might not be a rainbow colored triangle. Indeed, what you could do is, maybe the preferences happen to look something like this, where the red region is there, the orange region is here, and the blue region is there, you'll see that red splits blue from orange. So there's no rainbow colored triangle, okay? But that's not a realistic room preference assignment. Here is a pretty realistic room preference assignment. And the winding number is 1. So I start at red, and then I go orange, red, orange, blue, red. So I start at red, I go orange, blue, orange. Sorry, let me try that again. From red, I go to orange, back to red, to orange, blue to red. Okay, so I wrapped around once. And no matter how you color this in, you will have a rainbow colored triangle. So, oops. Maybe this is one possible coloring. You will still have a rainbow colored triangle. What might happen in this algorithm that we did is, as we do this walk along 1, 2 edges, you might walk along 1, 2 edges and start on the boundary and get back to the boundary, okay? But the winding number 1 means that there's an odd number of 1, 2 edges on the boundary. So you might start on the boundary and come back to the boundary, but since there's an odd number of 1, 2 edges on the boundary, there's another 1, 2 edge that you can start walking, where you then get to a rainbow colored triangle. All right. Yeah, that's where I wanted to end. So thanks a lot for your time and attention. We'll do public questions first and then private questions, I suppose.
Henry, I've got a question. I don't know if this is like a trivial question or whether you know this. So let's say that we want to get within epsilon of a true, quote unquote, true NV-free situation. Would it make sense to do, or would it like speed up the runtime, is say if we had like a relatively coarse discretization, and then we found, okay, in that discretization we found a cycle that satisfies what we want, an NV-free cycle.
Yep.
And then we said, okay, then we're going to do like recursively within that one, we're going to sub-discretize it, and then we're going to continuously sub-discretize it, rather than just discretizing it the entire graph so much at the beginning that just that solution would be within epsilon.
I think you're dead on. So I don't know exactly how the New York Times algorithm is making things faster, but I think that's a great, at least morally, that's got to be what they're doing. You know, like, let's say we found this is a coarse discretization, and we find this rainbow colored triangle. You see it right there, and we zoom in on it, okay? If we subdivide further and poll people along the boundaries, I don't think you're necessarily going to have this strict labeling where, you know, all the edges, the interiors of the edges were a single color, right? But it seems quite likely to me that you would have this winding number condition, right? It seems quite likely that you would have a winding number 1, in which case this fancier spurners lemma. So what I said, I'm not sure if it's strictly true, but my intuition is the same as yours. Maybe you have to be a little bit more careful, and I don't know, maybe you have to zoom in on a bigger, slightly bigger region or something.
Mm-hmm.
But I think that's great idea, and if you learn the details, I'd be interested to hear.
So I have a quick question. In higher dimensions, does the same argument work for always having a rainbow triangle? Or
Right,
is it like
this
different in some way?
Right, this following 1, 2 edges. Good question. We need to look at Francis Sue's article for this. Off the top of my head, I don't know, and it very much might be the case that it's quite a bit more complicated.
Are we, or would we be walking through edges or faces?
So yeah, let's try to brainstorm our own algorithm and see how good we get. So okay.
That point would be that the faces would be all but one color allowed, right? So then you'd be thinking about walking through the different faces of the tetrahedra.
Yeah. So, okay, right. So in higher dimensions, right, what this is going to look like is this front left face is where the red room is free, okay? So there's a red bulge coming out of that face into the tetrahedron. And then there's an orange bulge coming out of this face. And then out of the back face, there's a blue bulge, and out of the bottom face, there's a green bulge, okay? And so we were sort of walking along here, right? But there's a blue bulge in the back, and that blue bulge, you know, intersects the red, orange, and orange bulbs, right? So we sort of want to walk along a path going into the middle of the tetrahedron, where you're always in tetrahedra that have red, orange, and blue, right? So I guess red, orange, and blue. We're walking on tetrahedra that have two-dimensional faces that are red, orange, and blue, right? And we're hoping, you know, either you find another face that's red, orange, blue on an adjacent tetrahedron and you keep going, or the fourth vertex is green, and then you found your rainbow-colored smaller tetrahedron. Yeah, so Kyle, I think something like this will work, but I won't swear to it. Yeah, thanks, Michael.